experiments in the linear device and LAPD. And what I'm going to do is start just by telling you about the device and try to give you an overview of all the kinds of things, research projects that go on. So talk about the device, I'll give a few examples, advertise some works, I'll just show you a couple of results and point you to papers and ongoing things, and talk a little bit more in depth about a couple of things that I'm working on. In particular, I'll go into something, this one is something I've talked about before, I don't think everybody in the room has heard it, but thought it'd be good to review work on bias-driven flow in LAPD. But the new thing that we've been working on is it combines a couple of my interests in Alfvén waves and drift wave turbulence, is looking at nonlinear interactions between Alfvén waves and drift waves. And essentially, to give you the punchline, we've been studying beat wave interactions among Alfvén waves, where we see quasimodes driven in the uniform plasma. And in the case when we have a non-uniformity, we have drift waves in the system, gradient-driven instabilities. We find that we can use the beat wave between two shear Alfvén waves to interact and really control the drift wave instability. So I'll tell you about that. All right, so what is LAPD? It's a big linear device, okay? It's 20 meters long, roughly 17.5 meters, we say, for the plasma volume, and 1 meter diameter vacuum chamber. It's a user facility, so it operates kind of around the clock. It's a pulse discharge plasma, so it uses a hot cathode to make the plasma. The parameters you see are here. Nice thing about it for transport is that it is very big. Rho star in LAPD is 1/150 or perhaps 1/300 at high field. Helps to be cold, of course, that's why that happens. But it is big from a turbulence and transport point of view. And also, a lot of the data I show you is built up statistically. It has a 1 Hertz rep rate, and so we can gather lots of data on turbulence and transport. And it has similar parameters to tokamak far edge plasma, scrape-off layer. So it's a user facility. There's all kinds of things that are done with this facility. Motivations, as I didn't say, but was in the text there, come from space physics, astrophysics, fusion plasmas. Basic plasma physics that don't necessarily connect to that. So LAPD is really built for Alfvén waves. The reason it's 20 meters long is the wavelength of an Alfvén wave in this device is on the order of 5 meters. Maybe it can be less, okay? But this is why it's so big. And so there's been quite a bit of studies, starting with Walter Geckelman and his group. I'll talk about some recent work, very nice work by the Iowa group, which is looking at measuring in detail the dispersion and damping of high K-perp kinetic Alfvén waves and inertial Alfvén waves. And that's been done in tandem with simulations by AstroGeek, okay, by Greg Howes and his group. Also, recent studies on Alfvén waves in multi-ion plasmas that Stephen Sina's been doing. This is something that I think Ambrosio will talk about also, is there's been a lot of work on interaction of fast ions with turbulence in tokamaks, but also in this device that Bill Heidbrink has led. Space physics topics like electron phase space holes driven with electron beams, reconnection. Walter has gotten back into looking at reconnection in flux ropes. Shocks and Alfvén waves driven by laser plasmas. This is something that Chris Niemann has worked on with Walter. And then the last two I'll talk about, and this is work that I've been involved with, looking at nonlinear interactions between Alfvén waves. This is really motivated by some of the things we've heard earlier. MHD turbulence, where the idea is the building block of the cascade, at least from a weak turbulence point of view, is collisions between Alfvén waves. And so we're trying to study those processes in LAPD. And then there's been quite a bit of work looking at drift waves in this device and instabilities. All right, so what does the machine look like? Just to show you example profiles. Of course, the pictures don't come out well on this projector, but this is looking down the bore of the device at the visible emission from the plasma. Here's some example profiles. And so this starts at 12 centimeters, so you've got another 10 centimeters this way. Again, it's a big plasma. The density, the temperature, and this is a measurement of the flow using a Mach, a Gundestrop probe. And this is for a low field, 400 Gauss. But you see, I've marked here where the edge of the plasma source is. And so in this case, you have quite a bit of perpendicular transport. All this plasma out here is there because of perpendicular transport. The temperature here can range up to 10 eV. Typical is 6 to 8, 5 to 8 maybe. Now what I'm showing in addition here is something I'll talk about later, is a confinement transition that we see in LAPD associated with biasing. So what we do is we bias the wall and we drive a very strong flow in the edge, and we see a steepening of the profile that you can see here. Now generally you get a very flat core. Either, you can see here, maybe you go out to 15 centimeters. You have pretty flat region where you can study basic wave processes. And then you have the edge region out here. If we bias, you can get a flat density profile out to, say, 25 centimeters or so. And you typically see broadband turbulence in the edge of this device. All right, so let's show some example data, just to say how we go about taking data. What I'm showing you here is data from this experiment. And these are measurements in the cross-field plane of Alfvén waves. And so I'll explain what they are in a second. The magnetic field is coming out of the page here. And so I'm showing you measurements of magnetic field, the vectors of the field direction and the colors of the magnitude for Alfvén eigenmodes that exist in LAPD. These are cylindrical eigenmodes that are excited spontaneously, it turns out, by the plasma source. So the plasma source is a cathode and an anode that are separated by half a meter, and it turns out you can have a resonant Alfvén wave in that space. And they're driven up by the plasma current itself. And I'm just showing you, this is an M equals 0, this is an M equals 1. You see two counter-rotating current channels and a single current channel. And I'll use these later when I talk about Alfvén wave interactions, so I'll come back to it. But the way we take this data is with two probes. Okay, so it's not a big probe array. The typical way we do it is if we want to look at something like this, which actually is random phase. These are shot to shot. The phase of these waves is varying. You have a reference probe, and then you move shot to shot a second probe around in the plane. So this is like 1,600 points in this plane. It takes 12 hours to do it. It's done by computer control, and then you just correlate against the reference, and you can extract the structure of this mode. And this is what we use in trying to extract structure information from turbulence and other processes. Okay, so some quick advertisements about work that I think is of interest that's done on LAPD. I already mentioned this nice work by the Iowa group. Just talk about it a little bit more. Craig Kletzing has led this. Craig's a space physicist, somebody who's interested in auroral physics. And he's interested in kinetic Alfvén waves for electron acceleration in the aurora. And so he built a very specialized antenna that's able to very carefully excite waves with a certain K-perp, okay? And has used it to study damping and dispersion for waves in LAPD. Now, because it's low beta, K-perp rho s is what matters, as opposed to K-perp rho I. And that's the sound gyro radius. And so you can see here plots of the damping rate. I just picked out the damping. And these are plots actually from the paper from Greg House's student, where they compare Astro GK simulations against the data. And this is interesting because these waves are finite frequency. So in fact, the frequency of the wave is about half the cyclotron frequency. Yet the gyrokinetic description actually does a pretty good job. In the case of kinetic Alfvén wave, it turns out, is there a question? No, okay. In the case of the kinetic Alfvén wave, the damping actually is captured by collisionless. So if you actually put in the collisions, which are finite, it actually disagrees more. In the inertial case, the collisional damping is key. So here's the collisionless damping, and clearly, when you put in the collision operator in Astro GK, captures the damping pretty well. So this is very encouraging. We hope to continue comparisons. On to the next advertisement. So another thing that we've been doing, in fact, this is in collaboration with the Torpex group, and I think Ambrosia will talk more about this. And also on D3D, Bill Heidbrink has led this work, is trying to understand fast ion transport in turbulence. And this has relevance to, the motivations come from fusion, trying to understand transport of, for instance, alpha particles in fusion devices, and how turbulence driven by the by the bulk affects it. And so what we do is, there is turbulence in the edge of LAPD, but what we do is produce turbulence on demand, if you like, by putting a limiter in and generating a very sharp gradient. So we block the plasma production back here, and we get a sharp gradient and strong drift waves on the edge of that. And then Bill has a lithium-ion beam that he fires in, and we just measure the pattern of the beam and try to determine how much it diffuses in the turbulence. And we do see interesting things. This is a plot of the spread in the beam. So this is basically the width of this beam. So you have a spot that you start with when you inject the beam, and that spreads because of the interaction. This is several ports down from the ion beam. And what you see is that if you turn off the waves, and what that means is we close this plate, or open the plate, I should say, and get rid of this strong gradient. So now we just have a flat quiescent region. You see that the beam spreads according to classical diffusion, as would be expected. But if I now put it into this turbulent field, you see that I get much more spreading that's associated with the turbulence, but it's also energy dependent. And this is what might be expected based on orbit averaging. So you imagine that the higher energy the particle, the bigger the orbit, it'll average over the structures in the turbulence and basically not experience much in the way of transport. And you see a clear trend that's consistent with that. And this work is it's just been submitted by one of Bill's students. And it's being compared to theory. In fact, Frank Yenko is involved in this work also. Another aspect of the fast ion work that Bill's, yeah. So this is about 1 kilovolt. So 1 kilovolt lithium beam, well, okay, so sorry, in terms of, the numbers are here, I guess. So you go 1 kilovolt down to 400. The thermal plasma is 5 eV for the electrons. So you want to know velocity. I have to think about that for a second. And compared to, okay, compared to Alfvén speed. We've also studied, as you'll see on the next slide, interactions with Alfvén waves. So this beam is not able to get to the Alfvén speed. The Alfvén speed for the bulk would be more like 25 kilovolts. Okay, so these are low velocity with respect to Alfvén speed. But we have studied, again, this is led by Bill's group, interaction between this fast ion test beam and Alfvén waves. And in particular, looking at Doppler shifted cyclotron resonant interaction. And I won't go into all the details, but basically you get good agreement things that you expect physically. For instance, if you put in right-hand polarized waves, the interaction is minimal. Left-hand polarized waves, you get an interaction that you expect. This is a comparison between the spreading of the beam versus frequency of the waves compared to theory, to a Monte Carlo simulation, and you get very good agreement with that. Okay, so I want to move on now to a more extended advertisement of work that I'm doing. So I'll try to talk about two things. And this is work that I've talked about before and is a few years old now, but I thought it might be good to go through it again given the discussions on interaction of shear with turbulence. What we're doing in this experiment is using bias to drive flow. Of course, this has been done for many years, starting with Bob Taylor at UCLA on his CCT tokamak. And the idea, the way in fact, Bob was involved with this. The way that we do it is we bias the vacuum chamber. It's very simple. We don't use rings of any sort. We just bias the vacuum chamber relative to the source. We get a radial current. The radial current spins the plasma and look at what happens to turbulence in the profiles. The current here is carried by ions through ion-neutral collisions. And so that's where the torque comes from. All right, you already saw this. But essentially what we observe is if we turn the bias on the wall up beyond a certain threshold, you see a dramatic change in the profiles. And so this is much like an H-mode response in LAPD. Just to make a point, in this device, because it's so long, the perpendicular transport actually can compete with the parallel transport. you have the ability for the profiles to be set by perpendicular transport. And here we're actually shutting it off. It turns out that the profile before we bias is roughly consistent with Bohm diffusion. So if you were to do a transport model, which was done by Jim Maggs, that's what you find. And this new profile, after you transition, is consistent with classical transport, it turns out. All right, but all the flow is in the edge. The flow is in the edge because the drive, so the current path that drives the rotation comes from the wall and goes into the cathode edge. We're biasing relative to the cathode, so the current closes as soon as it gets to field lines that connect to the cathode. So all the cross-field current is in the edge region and not in the core, in the cathode region, and that's where you see the flow here.
What would be the correlation length in this case?
Okay, yeah, so the correlation length in this case is on the order of, in this is low field, 400 Gauss. It's around 5 centimeters is the correlation length. Maybe I'll show you a picture of it actually in a second. But.
This is on the lower
This is Mach number, yes. This is with respect, this is actually measured with a Mach probe. So the probe measures local Mach number. So this is with respect to the temperature profile that I see here. We see some heating, which actually we haven't explained yet, associated with the flow. Presumably that's heating on ions and then gets transferred to electrons, but we don't know. We haven't actually investigated that. Okay, so the threshold for this transition, so the first thing we thought of is of course, are we turning the knob on the flow and the flow shear past the threshold for suppressing the transport. And so we wanted to investigate this threshold. And what I'm showing here is just demonstrating that there is a threshold. This is the gradient scale length versus the wall bias. You can see as you go up in wall bias, you kind of drop into this new state, which is representative of classical transport in the edge. The reason for this is in fact flow penetration. It's not that we're turning the knob slowly on shear. The flow that we're driving using this process, I mean, this is still something we don't quite understand completely, but it doesn't penetrate in until you've reached a certain wall bias. And so actually these two plots here, so this red and orange are just below and just at the transition, okay? And these are if I push it harder. Below the transition, the flow is all out at the wall, and it hasn't really come into the edge of the plasma where the gradients and the turbulence exist. As I push it high enough, now this flow starts to penetrate in, and then it just sits on the edge of the cathode. The shearing rate, which I'm plotting here, sits right on the edge of the cathode where the gradients are and can interact. So the physics of the transition is really flow penetration and not necessarily overcoming a shearing rate. The point is that the shearing rate is roughly the same before and after the transition. It's just in the wrong spot. And the shearing rate is more than enough to suppress the turbulence. I have a slide on that, but I've taken it out to save time. So what happens to the transport? So if you make measurements of the transport flux, we can do using the standard technique, probe technique. This is just making measurements of the electric field using floating potential and density fluctuations and looking at their correlation. What you see is that this is the unbiased case. As I go through the threshold, which is around 100 volts, you see that the measured flux actually does get suppressed. In fact, reverses as I go to much higher bias values. So that we are affecting the turbulent transport. Just to make a quick diagnostic point, we don't make good measurements of transport flux or electric field fluctuations once you're on field lines that connect to the cathode. The reason is there's a lot of fast electrons. There's primary electrons there. And we believe this interferes with the floating probe ability to kind of pick up these fluctuations. And so therefore, we don't believe this reduction here is real. We think that's a diagnostic effect. But nonetheless, in the region where we trust the measurement, you do see a suppression of the transport flux. So why is it going down? So there's several, maybe I should show this first. You want to calculate transport flux, you can see the punchline there, but the transport flux you can kind of write out in this way. It depends on the amplitude of density, electric field, coherency between them, and their cross space. So you want to evaluate all these possibilities. First thing is that the amplitude actually, in this case, you don't see strong suppression of the turbulence. It actually is, the amplitude of the turbulence remains high even as you transition. So this is below transition, and this is now well above transition. And you see there's, as the profile is steepened up here, you still get very strong fluctuations. Now, you know, over the whole profile, you've reduced the volume average fluctuation amplitude, but there are still very strong fluctuations on this gradient in the case when there's classical transport. So this amplitude suppression is not what explains the loss of transport. Now, I'm not showing you dynamics. Again, that's a slide that I dropped out of this, but there is a transient suppression. Okay, so maybe this is similar to some observations in H mode, where you see the fluctuations first get suppressed, then you get profile steepening, and then they come back. Okay, and there's a little bit of behavior like that in this system too. But in the steady state, where you have no turbulent transport, there are very strong fluctuations. All right, so this doesn't necessarily directly connect to that formula for transport flux. I mean, it can be connected, but another idea is that associated with shear suppression is that you're basically decorrelating the turbulence. You're changing the spatial size of the eddies through the shear. And so we can evaluate that directly by measuring the correlation function in the turbulence using the same technique I mentioned earlier. We have one fixed probe, and then that we have a phase reference for, and then we move another probe around and calculate the correlation shot by shot. And that's what I'm showing you here. So this is the correlation function in the unbiased case, and again we're looking at the edge of the plasma over here. And you see a correlation function that almost looks isotropic. This is the azimuthal direction and the radial direction here. You see some evidence of a negative lobe, and so you might call the radial correlation length a little bit bigger, but it's on the order of 5 centimeters, as I mentioned. Now what happens in the bias? So this is now in the steepened profile transition case. You definitely see an effect of the shear flow. Okay, the correlation function is sheared. However, I mean, you wouldn't argue that in this case that you have broken up, decorrelated it radially. Okay, the radial structure size is still comparable. You might make an argument that transport is decreased because you have to go all the way around this sheared eddy, but really that's not enough either. And so the question is, what is happening? And you saw this slide already. The answer is that you're really modifying the nature of the turbulence. It's now very different in the sense that the cross phase between density and potential is what's modified strongly. So I'm showing you power spectra for density, potential. This is ISAT for electric field, actually. And then coherency. Now, there is some reduction in amplitude. In fact, the electric field amplitude goes down more, but the overall change in the amplitude is not enough to explain the tremendous drop in transport. The coherency actually goes up when we do this between density and electric field. But what changes dramatically is the cross phase. You start out with cross phase that's perfectly aligned for transport. This is because of dominance of blobby transport. That's something that Ambrosio will talk about. And as you go up through the transition, you reduce that to near zero, which would be no transport. And interestingly, as we go to very high bias, you see the phase reverse, indicating inward transport. And this is something we're still not sure if we believe. Okay, there's some evidence that there is some inward transport, but it doesn't quite match transport modeling. You'd have to have quite a source of density out in the edge for this to make sense. Yeah?
What's the ion gyre radius in centimeters?
Ion gyre radius in this case is around 3 millimeters, so 0.3 centimeters. Yeah. All right, so moving on, so move on to a quick advertisement, then I'll take the last 15 minutes and talk about the very new thing that I mentioned early on, the alpha wave interaction. We're very interested in using simulation as a tool to understand what's going on here. So we're trying to do simulations. We started with Brzezinski fluid simulations. So we're using the Bout code, which was originally written at Livermore. And now Ben Dudson in York has rewritten it in a very nice way. It's now called Bout++, so we're working with Ben also to simulate LAPD. We've gone through it turns out it's not so hard to simulate LAPD in Bout because of the flexible geometry specification. But we've had to add a few things to make it consistent with cylindrical geometry and handle the biasing experiments. So we've done verification studies, and it works very well. We, in the process, learned more about the linear instabilities in LAPD, which was a good thing. I don't have the paper reference here. That's been submitted, as well as what I'll show next. I mean, the real question here, I mean, we can provide the detailed measurements we can do in LAPD should really challenge the simulation codes. The question is Rogensky enough to explain LAPD? Certainly in the case of Alfvén waves, you know that collisionless effects are important. We just saw that in the kinetic Alfvén wave case. However, it's somewhat collisional. The mean free is really collisional. Okay, the mean free path is around 20 centimeters. And so it's not collisional enough that you could completely rule out the possibility that kinetic effects are important. And I think this process might help delineate where the fluid code might break down. And of course, we're very interested in gyrokinetic and gyrofluid simulations of LAPD turbulence. We'd love to see AstroGeek simulations with gradients in them for drift waves. And just to show a
description.
right, so there's other things.
There's more things.
Fair enough.
In Rogensky.
That's right. That's right. So okay, so we're not necessarily just looking at kinetic versus fluid. Right. Right. So here's the movie. I guess it comes out okay. So I have to show a pretty movie, not necessarily conveying a physics message here, but this is what the simulation looks like, taking a piece of LAPD. We've spent some time trying to figure out how to do these simulations. It turns out that getting the plasma sources and sinks right is very important to maintain profiles. So in this case, we've added an ad hoc source to keep the profile close to experimental. I'm working with Barrett Rogers and Paula Ricci, who have a code where they're putting in first principle sources, and I'm very interested in that, and in particular seeing if it can predict flow profiles right. This simulation predicts strong zonal flows, and that's what this plot was showing. But we haven't yet. We see a certain flow profile in LAPD that this does not match at this point. Actually, my student David Schaffner will be here next week, and he'll talk about the flow scalings and turbulence in LAPD next Thursday. But it's very interesting because if you look at the spectrum of the fluctuations that this predicts and just compare it against LAPD, it actually does a pretty good job, probably too good to be true. The black line is LAPD, and the various other lines are bout simulations with different neutral collisionality, with different resolution, and it actually does a very good job of matching the spectral shape. I have to make sure to point out these are scaled. The amplitudes are close but not dead on, so the curves are actually a little bit below the experiment. But the spectral shape is good. We've discussed how spectral shape might not be the most important thing in the tokamak simulations, for example. The correlation function is a little bit longer, so here's the data that we're comparing against and what's that about. But it's encouraging, and we're going to continue along this route. And the near-term focus, as I said, is kind of understanding the flow in LAPD and how it's generated. Yeah?
Is this ISAT or density?
This is ISAT, yes, this is ISAT. Yep. All right, so now on to the last bit, which hopefully I can wrap up in a little over 10 minutes. We've been interested in studying Alfvén wave interactions. As I mentioned, it's motivated by the MHD turbulence problem. So we've been basically colliding Alfvén waves. This is old. Just a quick review. We observed a beat wave interaction between two co-propagating Alfvén waves. So this maser, this cavity source that I mentioned earlier, we've done it with antennas also, so this is not the only representative data. You launch two Alfvén waves at slightly different frequencies because they're dispersive. So you have dispersion that comes from finite K-perp and also from finite frequency. They have different phase velocities. They can pass through one another. You get a beat response in the plasma. So what I'm showing here is a case where we have one dominant Alfvén wave that's coming out of this cavity. And what I'll show next is a case when we have two strong waves coming out together at different frequencies. Now the spectrum's a bit of a mess here, but if you look in the steady state case, you see a number of lines here that are sidebands around this m=0 and m=1 mode that you can see here clearly. And if you look at low frequency, you see a very strong response in the plasma at the separation frequency, at the beat frequency. And this really surprised us because these waves, although they're big for LAPD, 1% delta B over B, the pointing flux is as big as the heating source, it turns out. So these are big waves. But the this is a quasi-mode, it turns out. This is not a linear plasma wave that's driving. There's a 10% response at low frequency. But this is consistent with a quick nonlinear theory. It's really due to nonlinear ion polarization in the beat wave, and the details are here. Now what I want to talk about now, sorry I didn't give you too much details about this, but we recognize that the frequencies that we can access in these kind of experiments are in the 10 kilohertz range, and this is right in the middle of where drift waves sit in LAPD. So we were interested in, can you have interactions between alphane waves and drift waves through this beat interaction process? We wanted to do a simplified experiment. So instead of looking in the natural edge of LAPD, where I showed you we have nice broadband turbulence and we've characterized transport, we wanted to look at a simple system. And so what we did is we looked at drift waves or gradient-driven instabilities. As I'll say, it looks like possible that in the mode we're looking at might have flute-like characteristics rather than drift wave, but I'll come to that. We make a density depletion. So we just block plasma production, and you have a hole in the plasma, and around that hole you get an instability. And it's a nice coherent mode. And then we launch 2 alphane waves from an antenna at the other end and change the frequency and see what happens. And so this has actually just been accepted in PRL. There's an archive reference there if you want to look at the details. All right, so first, what do the fluctuations look like on this depletion? So this is what the depletion looks like in the 2 crossfield directions. This is just the pressure, actually, in the depletion. You see fluctuations that grow up on the edge of the depletion that are shown here. The pattern's not perfectly symmetric. There's some variations in the background density that cause localization. But if you look at this mode, it's fairly coherent. You see something around 6 kilohertz in harmonics. And if you measure the correlation properties of the mode, it's an m=1 mode. So we spent some time trying to, we assumed we were going to excite drift waves. It turns out this mode has some character like a drift wave. Delta n over n is very close to Boltzmann. However, the density potential crossphase that we measure in this wave is 180. So this is completely inconsistent with the drift wave. So we've done some modeling, which I'll just mention briefly. If you do the modeling of the profiles, we have a cylindrical eigenmode solver that has been developed for the bout work that we calculate modes in this case. You see that both drift wave types, so that's going to be the fundamental mode, n of a half would be drift wave, and flute modes, which would have nz equal to 0, can be growing. The drift wave should have the faster growth rate. However, it looks like this is a hybrid of those two. We're not quite sure. But we have an instability, I guess I'll put it at that, that we're looking at interaction with. And here's the most important picture, I guess, which is what happens when we put in this beat wave. So what I'm showing you is the measured power spectrum in a number of experiments. So each vertical stripe is an experiment where we change the beat frequency of the alphane waves. Okay? And so what you can see here is that the instability is sitting here, okay? And the beat wave, we're changing along this line here, okay? Now when we first did this, I was thinking that maybe we could resonantly drive the drift wave, and you do see, or the instability, you do see a brightening around the instability frequency, okay? And you can see that here. This is a cut through the beat wave power, and you can see it brightens around, a little bit downshifted, but around the same frequency. But the surprising thing that we saw is that as we drive this frequency a bit higher, you seem to turn off the original instability, and what is left behind is just the beat response, okay, as you can see here. And not only that, you see it kind of quiets down in a number of regions in frequency space, and I'll show you a better picture of that in a second. And as we go up in frequency, eventually the instability turns back on. Okay. Now, as I'll show you, this is a nonlinear phenomenon. The threshold, there is a threshold in amplitude. You have to get the beat wave up enough for this to happen. All right. So first, just to show you line spectra. So now this is line spectra taken kind of here and then here through the minimum of the instability. Now you see, there's still there's a sign of the mode trying to come back on here. But what we see is that the dominant response is in the beat frequency, which is around 8 kilohertz here. But the other interesting thing, although this is mostly a coherent mode, there are some broadband background fluctuations associated with this, as you can see at low frequency. Presumably this is some nonlinear drive through saturation of this instability that drives up these low frequency fluctuations, and you can see they drop out. At least they get reduced when I'm doing this. So the surprising thing, the net result is, even though I'm putting energy into the system with this wave, the net fluctuation amplitude goes down when I do this in general. If you look at this mode, so if I go back, I really see two brightenings, right? So I see what looks like a brightening, a resonant response here, and then up here, okay? And it turns out, what looks like experimentally is those two are actually two distinct eigenmodes. You're coupling first to the m equals 1. This is without the beat wave. This is if I drive it around the same frequency, I get an m equals 1. If I go to the higher frequency, I'm actually coupling to an m equals 2, it turns out. Okay, so what I'm doing is turning on this linear mode that wasn't driven or wasn't there before. It wasn't unstable. I mean, you predict it to be unstable from the simple theory, but it wasn't active during the experiment. So further proof that we're coupling to linear modes in this case. This is different from the previous experiment where we're just broadcasting these waves into a uniform plasma. We get a quasi-mode, which is not a linear mode. In this case, we do see evidence of a linear mode, not only what I showed you before, but there's also evidence of a ring up. So basically, you're putting energy into this resonance, and it takes time to saturate. And then as you turn off the kinetic alphane waves, you see a ring down. And this is not what's observed with a quasi-mode. Basically, when you turn off the waves, the mode's gone. Okay. Now, another point to make that I don't think I have on the slides is that the amplitude required to get this to happen in terms of the alphane waves is much, much less. So I had to go to 1%, which again in LAPD are whopping alphane waves, to get the quasi-mode visible. Well, it was up to 10%. But to get 10% fluctuations here, I can go down an order of magnitude or more. 0.1% delta B over B is enough to actually get a substantial response into these linear modes. All right, so about the threshold then. So what we see is that I'm plotting here the amplitude at the instability. So this is at 6 kilohertz. This is the amplitude of the beat wave fixed at 8 kilohertz. Okay, and so what you see is that as I go up in amplitude, this is normalized to the amplitude of the drift wave, or roughly speaking, the peak amplitude of the drift wave, or instability. What you see is as I come up to about 10% in the amplitude of the instability, I start to make an effect. And certainly as I go up just a little bit above that, you can really suppress the instability. So this is not a huge perturbation. I'm putting in fluctuations that are comparable to the original or less than by a factor of 10, the original unstable amplitude. Now a couple of interesting points. First of all, this dotted line is the line where I make the beat frequency 0. So this is just looking at the effect of the alphane wave on the instability. And there is an effect that causes some suppression. Okay, so I have to point that out. We believe this is because of heating. Okay, so there is some heating that happens with the alphane wave that we think modifies the profiles and changes the fluctuations. But the dominant effect is the frequency-dependent effect. So if I go to this 8 kilohertz, I drop this way down. At other frequencies, it's closer up to here. So we believe this is really a nonlinear control using the beat wave that's most important and not single alphane wave interactions and heating. The other interesting thing is that the response to the beat wave saturates. And this is something we didn't see with the quasi-mode. We could basically turn the knob. It wouldn't quite be bilinear. But essentially, you turn the knob on the alphane waves, you keep getting more quasi-mode amplitude. Here, as I boost this is the amplitude of the alphane wave through the antenna current, it saturates at some point. So it's as if I'm transferring what energy was going into here, into there, and somehow I can't go much further. And so that's another interesting observation we have yet to explain. And I think this is the last bit. The other thing that's interesting is that the width. So if you go back to this plot in the beginning here, there's a certain width over which I have control. If I go too far in frequency, it comes back on. And that's also amplitude dependent. So you see here, as I go up in kinetic Alfvén wave amplitude, the width over which I have this control expands, okay, with amplitude. Oh, I did have one more bit, okay. One thing that we did try, I'm interested in how it couples, okay. How does this beat wave couple to the drift wave? It turns out that these are co-propagating Alfvén waves. When they're co-propagating, the beat wave, the idler, has a very long wavelength. It's actually machine size for LAPD. And that's consistent with the instability. So if it's fluid or drift wave, either way, it has a long wavelength along the field. So what we did was we turned the antennas around and did a counter-propagating interaction. And this will have a much shorter wavelength. In fact, that's the interaction that can couple to sound waves. And what you see is that this behavior is not present in that case. So it really does matter that the beat wave has a long parallel wavelength. And what I'm showing you here is just the response in basically the beat wave as it resonates around the instability. In the counterpropagating case, there is some response, but it's much, much reduced, and you don't see this control behavior. So it does matter what the parallel wavelength of the beat wave is. All right. And I guess there's a couple more just to say a few words to connect this to other things. There's been a lot of very good work by group Mirabel and Veneta machines. Thomas Klinger's been involved in directly exciting drift waves using antennas and electrostatic or electrodes and current straps, basically. And they found that they can directly drive drift waves using these structures, using either current loops that evanescently couple energy into the plasma or electrodes. And when they do this, they can actually control the spectrum. So here's a case where you have kind of a semi-coherent instability spectrum, and they put in a drive at a frequency that's slightly different, and they can really control this spectrum quite well using this approach. And there's been quite a bit of work since this, extending this idea. And so I believe this is very similar to that. However, the difference is we're using now RF waves, Alfvén waves, to do this control rather than electrodes and saddle coils. And the question I have is this kind of, you know, it's maybe early in the game, but it's useful to pose it anyway, maybe. Is this a process that might be portable to control of instabilities in a fusion device? And using RF, using Alfvén waves, seems to be a little more likely as a candidate than electrodes. In particular, I'm interested in whether or not, I mean, there's been a lot of work. Ambrosio really led this at JET, looking at ICRF beat waves. And it was used to excite TAEs in that case. And there's been a lot of recent interest in this. And, on ASDEX, there's a new result where they're exciting TAEs with ICRF beat waves. On JET, almost every RF shot has an ICRF beat wave in it, it turns out. It's uncontrolled in frequency, but it's there. But it tends to be high frequency. And so the question is, can you do something similar with ICRF beat waves? Could you kind of tune the beat wave into the ITG, TEM, whatever you like, frequency range, and see if there's an interaction between the beat wave and the turbulence? This is something I'm interested in trying to do. And with that, I'll stop. This is my summary, so I don't think I need to say it. Okay. It's very difficult. Yeah, I mean, this is something that we should be doing, because it's certainly to distinguish between these different modes, that's the thing to do, right? However, it's not easy. I mean, you've got a 17-meter long device discerning between k equals 0 and k equals finite. It's very difficult given the aspect ratio of fluctuation. So, and also, I mean, other people have done this, and actually maybe Ambrosio can comment on how he does it, but I'm always wondering about how you get this, because it shouldn't be a propagating mode. It's going to be a standing structure. So really what you're looking at is envelope, if you like, or the amplitude as it goes to the wall, and not really a phase measurement. So I don't know, maybe you can correct me on that, but I'm always curious about how you do that measurement.
It's very boring to do.
I agree. I mean, I think there's other ways to go about it. I think in distinguishing these two, the eigenmode profiles are probably the way to go, because the shear flow and the density gradient that are in this system are slightly offset. And so what I think we really need to do is look at the predicted eigenmode structure and then see how well it agrees with what's there.
And how about the dominant K per rho s? I mean, where do you sit?
So for the natural turbulence, we sit not a little bit below the peak, I mean the edge turbulence, not this little depletion. So the edge turbulence, if you calculate linear growth rates, you predict a peak at about m equals 20, and we tend to see 15 and a little bit below that, but it's in the ballpark. So K rho s there is, I have a plot, but it's of order half, maybe.
Questions? I myself have a question
Sure.
about your flows.
Yeah.
You showed Mach numbers of unity.
Yes, it's quite strong. I mean, that was a case where we really turn up the bias until we start arcing, really. That's as high as we can go. But you can get Mach numbers of order unity. And in that case, I didn't show the data here, but when you get to that type of flow, you start to see new fluctuations come in that are possibly rotational interchange. There's other stuff happening, but we don't have to go there to get the suppression. It happens as much as you saw, the shearing rate way down here was enough, and that plot was way up there. So. Yeah, maybe. I don't know. We haven't, if you believe the Mach probe, it says we're going at 1 and a little bit above. And it's a question if you believe that. But so far the limitation has been on electrical issues, arcing, and so forth, and not on not saturation in the flow we're able to drive.